Hey guys, in this video the brilliant Mr. B is going to be taking you through plotting lines for your A-level maths. Now there are lots of different examples in here, work through at a slow pace, and if you check the pinned comment then you can jump between the levels. Moving on in your own time with no pressure from anyone else watching. Now if you want more questions to go with this, then there are loads and loads and loads just waiting for you over on my website, so you can really get to grips with this skill.
Two methods to plot graphs. The first method is to substitute and get all the accurate points for the graph. The second method is to actually look at the equation and get facts from the equation. Now we'll look at both, but let's look at substitution first. So we have y is equal to x squared minus 6x plus 8. So what we want to do to sketch this graph is we want to take different values of x. So we want to say that perhaps x could be equal to 0 and 1 and 2. And we'll get an idea of the shape of the graph in those areas, and then might want to look at negative numbers as well, like -1 and -2. Now that might actually be enough to sketch the entire thing, but what you want to do as well is just leave a bit of space for more of these if you need them. So I'm going to substitute, we're going to swap every instance of x with what we're looking at. And for the first one, we're looking at x is equal to 0. So y is going to be equal to 0 squared, take away 6 lots of 0, plus 8. And if we do all of that, our answer is going to be 8. That means we can say that the coordinate 0, 8 is on the graph with an x coordinate and a y coordinate. So let's plot 0, 8. Now let's substitute 1. So again, every single x is going to be replaced by a 1. So we'll have y is equal to 1 squared, take away 6 times 1, plus 8. So altogether that'll be 1 take away 6 plus 8, and 1 take away 6 plus 8 is going to give us 3. That means we're going to have the coordinate 1, 3 on the line, and we can plot that. Let's have a look at 2. So again, every single x will be replaced by 2, leaving us with y is equal to 2 squared, take away 6 lots of 2 plus 8. That's going to give us 4 take away 12 plus 8, which altogether will give us 0. So the coordinate 2, 0, which we can plot. Let's have a look at some negative numbers as well. So let's look at -1. That leaves us y is equal to -1 squared. And with negative numbers, put brackets around as well, just in case. So that's going to give us -1 squared is 1. Then it's going to be take away -6, that's plus 6. And then plus 8. Altogether, that gives us 15. And the coordinate, -1, 15. Now, I've only got a 10 by 10 graph here, so that's going to go off the side of the page, which means that looking at -2 is going to be kind of pointless. So why don't we kind of carry on looking at positive numbers and look at x is equal to 3. And this is typical of what you'd have to do, where you just adjust what you're substituting based on the kind of results you get. It might be that some substitutions are not going to be helpful. Now we have y is equal to 3 squared, take away 3 lots of 6, plus 8. That's going to be 9. Take away 18 plus 8, which is -1. Giving us the coordinate 3, -1. Now you might be starting to see the curve emerge here. Let's keep going. Let's have a look at x is equal to 4. Swap in the x values with 4s. Give us y is equal to 4 squared, take away 6 times 4 plus 8. That's 16. Take away 24 plus 8, which altogether is 0. That gives us the coordinate 4, 0. 4 for x and 0 for y. And let's plot. Now, at this point, we're done because we repeated a kind of a previous value with a previous y value of 0. And if we start to draw this and make sure you've got a curve going through these points, coming down, it reaches its minimum point and then it starts to come back up. Now, this is going to be symmetrical, so we can kind of see the heights of the next two coordinates without actually writing them down. So 5 would be at 3 and 6 is at 8. Again, we can just see the symmetry in our answers here. So we can see we've had 8, 3, and 0 on one side, and then we've got 0, 3, and 8 on the other side, with a -1 in the middle being the minimum point. Then, of course, the 15 was out of sequence. So now we can draw the rest of this, and we've got a sketch of our graph, and it's pretty accurate using the method that we've used. Now, what I want to show you here is there is a faster way to get some of these coordinates, and it's by inspecting the equation itself. So we've got y is equal to x squared minus 6x plus 8. Well, you can factorize this. X times x is x squared. How do we get the 8? That would have to be 4 times 2. And how do we get the -6? That would be -4, take away 2. So we have factorized. If we then solve that for it being equal to 0, we would have x being equal to 4 or x being equal to 2. Now, what does solving actually mean? Well, we're saying that y is equal to the expression which is equal to 0. So y is equal to 0. By solving it for 0, we're looking at positions on the curve where y is equal to 0. And now, where is y equal to 0 on a graph? Well, it's the x-axis. At all points of the x-axis, y is equal to 0. And you can see there's 2 coordinates on the x-axis. So what were those coordinates? Well, we had 2, 0, and we had 4, 0. Now, those 2 points should be familiar because those 2 coordinates we actually got from our substitution. We got 4, 0, and we got 2, 0. So by doing a factorization, your answers are actually going to be 2 of your coordinates, with y being equal to 0, and then x being your 2 alternative answers. So that's the first thing you can do by inspection, just by looking at what you've got. There's another coordinate you can find really easily as well, and that coordinate is to do with a +8. Now, this +8, this is the y-intercept, which you might remember from straight lines. It's also a y-intercept in other kinds of lines. And so if you've got a +8, that means that you're going to have the coordinate 0, 8, which we can see we have on the line. And so we can see that a third one of our substitutions was almost a waste of time because we got it from just inspecting our original equation. Now, the question from this is, could we have sketched this from just those 3 points? And in a way we could have. We could have got a really good estimate. Perhaps you wouldn't have known how far down to go, with going far down as -1. And then perhaps we'd be a little bit shaky in between the green and the blue coordinates there, because we've got an extra coordinate in the middle. So it wouldn't be as good of a sketch, but we could do a sketch without doing any substitutions. There is a third piece of information we get from this, and it's by completing the square. Now, if we complete the square, so what we want to do there is take our x squared down to x and half our -6 to -3 and make all of that squared. We multiply that bracket out. As long as we took away 9 from it, we would get exactly the same thing. With a -9 coming from 3 times 3 is 9, which will give us an extra 9. If you're not sure about that, have a look at the video about quadratics. We'll go through completing the square. Now, we are still adding on the 8 at the end as well. So we complete the square. Altogether, what we're going to get is x minus 3 squared, -9 plus 8, is -1. And you might notice that when you complete the square, we've got a 3 and a 1 in our completing the square form. Now have a look at our substitutions. We've got a 3 and a 1 in 2 places. We've got one here, which was the minimum point. It was the bottom part of our curve. Now, what you need to know about completing the square is that when you have a look at the 2 bits that are highlighted, the one on the inside of the bracket, the negative version of that is your x coordinate, and the one outside the bracket, the positive version, is your y coordinate. So that's going to give us the coordinate 3, -1. And so now with these 4 values, we could actually get a really good sketch of the curve without doing any substitution. So we have 2 possible methods. You are expected to know both, and even using a mix of them is probably going to be the fastest way, where it might be that you can get these 4 points from doing the kind of inspection methods we've gone through, and then perhaps if you're not too sure, you could do a couple of extra points using substitution. So now let's try and do a sketch without any substitution. So we've got x squared plus 3x. You'll notice there's no y-intercept here. It's essentially going to be a +0, which means that we're going to have the coordinate 0, 0 in this. This is where the curve crosses the y-axis. Next, we can factorize this. Now, again, with no +0 on the end, we can't put it into 2 brackets. What we can do is we can take x out of both terms. We'll give us x, and then x plus 3. If you multiply that out, you'll get back to our original expression. Now, if we said this was equal to 0, x would have to be equal to 0 to make the whole thing 0, or x would have to be equal to -3, because we make the bracket have a 0 on the inside. We multiply by 0, so we get 0. So if x is -3, we've got -3 plus 3, which is 0. This gives us 2 more coordinates. We're going to have x is 0, so y is 0, and we're going to have x is -3, so y is 0. Now, for this question, one of those is a repeat of the one we've got. So it means that the y-intercept and also one of the x-intercepts are the same thing. But in the previous question, we did have separate y-intercept and 2 x-intercepts. Then we have the -3, 0. So we can plot there as well. Now, we're probably going to want the minimum point of this. So let's complete the square. So completing the square, x squared becomes x, We're going to have the 3. Let's call it 3 over 2 for now. And then we're going to have to take away the 3 over 2 multiplied by itself. And again, have a look at the video for this if you're unsure at what's going on. But we're going to be taking away 9/4. Now, to simplify this, there's a plus 0 on the end, so that doesn't change. So now we've got our coordinate. So it's going to be the negative version of x, so negative 3 over 2. And then the y coordinate's going to be negative 9/4. And that's going to be a little bit hard to plot. Let's turn them into mixed numbers. So 3 over 2 is 1.5. 9 divided by 4 is going to be 2, remainder 1. So 2.25. That'll be negative 2.25. Again, we might want to write these as mixed numbers rather than decimals. So let's try 1.5 like that. So now we can find these. So we're going to go backwards 1.5 and then down 2.25. And the bottom, the minimum point will be roughly wherever it's highlighted in pink. So from that, we could get an okay sketch of the curve, and I'll give it a go. It's going to be something like this. And the issue here is I don't really know where to put the curve towards the top end. So what I'll do now is I will do a couple of these using substitution. Now you have a look at what we've got. We've got 0 and we've got negative 3. So why don't we have a look at 1? So we have y is equal to x squared plus 3x. So if we take x to be equal to 1 and replace the x's with 1s, that means that y is going to be equal to 1 squared plus 3 lots of 1. Well, altogether that's going to be 4. So we can plot the coordinate 1, 4. 1 across and 4 out. And actually my sketch wasn't too bad. I did go through that point. And symmetrically on the other side, going back by 1, it'll also have a height of 4. So that wasn't too bad actually. Well, we've done 1. Let's have a look at 2 and see how accurate the top of this was as well. Again, it is a sketch. So as long as it just fits the information that you have, then you're not going to do too badly. It doesn't have to be perfect. So we have 2 squared plus 3 lots of 2. That's 4 plus 6 is 10. So we would be plotting 2 and 10. So that's going to be here. Now this is where you can see that my sketch actually was a little bit too far away. So I'm just going to correct that now. I'm going to rub off what I did at the top end and correct it. But in an exam, if you're doing a sketch, you're not going to be penalised too harshly for being a little bit off up there, as long as the things you can get from inspection are correct. That means that you've got to be crossing the x and the y axes in the correct places. So again, the 3 coordinates we found at the start. And now we've got a really accurate sketch. And I would still call this a sketch because my curve isn't the smoothest. So what you might want to do now is maybe rub it out again and just have another go trying to get it nice and smooth. So let's have a look at one more quadratic and let's see how far we can get without doing any substitution. So we've got the plus 6. So the plus 6 means that we're definitely going to be going through 0, 6. It's the y-intercept. It's where we cross over the y-axis. Then we can factorize, and if we factorize, this should be x times x is x squared. Then what the 6? Well, I think it's probably going to be 3 times 2. It's going to make us 6. So to get the 5, that's going to be 3 plus 2. So we've solved that for y being equal to 0, then x would have to be equal to negative 3 or negative 2. So we know we have 2 more coordinates now. We have negative 2, 0 and negative 3, 0. Now, they're so close together, there's probably not too much point looking at the minimum point. That's going to be just below those 2, but we'll have a look at it anyway. So we'll complete the square. X squared becomes x. We want half of the 5 halves, and then we're going to take away the result of 5 halves multiplied by 5 halves, which would be 25 quarters. And add on the 6. So to simplify this, well, what's 25 quarters going to be? It's going to be 6 and 1 quarter plus 6. So altogether, that's going to give us 5 over 2 squared. So a negative 6 and a quarter plus 6 is going to leave us a negative quarter. That's going to give us our coordinates. We're going to have a negative version of what's inside the brackets and a positive version of what's outside the brackets. Well, not positive, but the same symbol. You're just reversing the symbol inside the brackets. And then 5 over 2, let's write that as a mixed number. That's going to be 2.5. So we're going to go 2.5 back, and we're going to go negative a quarter down, which, as you can see, is really, really close to those 2 blue coordinates we found. So with this now, we could get a decent sketch of this. So I'm going to have a go. So it's going to be something like this. Again, the most accurate part's going to have to be the 3 coordinates we found at the bottom. We're going to go through the green coordinate as well. So something like that. Now, I don't think that's quite round enough. It's a little bit too pointy. So what we need to do now is do a couple of substitutions to check kind of how smooth this needs to be. So I have y is equal to x squared plus 5x plus 6. So I think looking in kind of in between the blue and green coordinates, looking at 1 is going to be helpful here. Let's take x to equal 1. Y equals 1 squared plus 5 times 1 plus 6. Well, altogether that's going to be 12. Now, 12 will go off my graph, but it's going to be somewhere, roughly around about here. So you can see my sketch isn't too far off there, actually. Thinking about it, what I actually wanted is -1 here. I want to be in between the green and blue coordinates. So let's look at -1 instead. This should be more helpful. So y equals -1 squared plus 5 lots of -1 plus 6. So that's going to be 1 take away 5 plus 6, which is going to give us 2. So that's going to be the coordinate -1, 2. And -1, 2 is going to be roughly one point in the blue coordinate there. And you can see again, my sketch wasn't too far off actually. So again, you can get a really good sketch just by inspecting the equation you're given, looking at the y-intercept, looking at the solutions to factorizing and solving the quadratic, which are the x-intercepts with a line just through the x-axis, and completing the square to find the minimum or maximum point. But then if there's anything you're not sure about, you can do a couple of substitutions as well. But you can see the last couple of questions, I only did 2 substitutions, whereas in the first question, I had to do, 6 or 7 substitutions, which was a lot more work. Similar techniques can be used on cubics as well. So for example, I can see straight away, we've got a +6 at the end, which is the y-intercept, which means that 0, 6 is going to be a coordinate on this line. Then we can factorize the cubic. Now, I'm not going to go through factorizing cubics in this video. We're going to have a look at the video where we do algebraic long division and factorize cubics. But if you were to factorize this, you would get x plus 2, x minus 1, and x minus 3. Now, if you solve that equal to 0, you get values for x of -2, -1, and +3, which are going to give us some coordinates. That's going to give us -2, 0, -1, 0, and 3, 0. So not only have we got the y-intercept in green, we've got the x-intercepts in blue, and we have 3 of them. Now, actually, I've got one of the signs wrong here, so that 1 should be negative actually, which will give us a +1. So then we're going to have -2, +1, and +3 as our x-intercepts. Now again, we could do a pretty decent sketch of this. It's going to look something like this. And this is pretty bad for a sketch actually, but you get the idea. But I'm going to rub this out and do it properly in a moment. So what we need to be doing now is looking for the kind of minimum and maximum points. So I'm just going to highlight those in pink to find what this coordinate is and this coordinate is. Now, there's a really good way of doing that differentiation. Let's take our line. Y is equal to x cubed, take away 2x squared minus 5x plus 6. And if we differentiate it, it's going to give us an expression for the gradient. So when you differentiate, again, you can watch the differentiation video for more information on this. We'll bring down the powers. We'll have 3x, bringing that power down. But when you do that, you've got to reduce the power by 1. If you bring the power down, there's already a number there, multiply them together. 2 times 2 is 4, then reduce the power by 1 from 2 to 1. Then with 5x, we'll bring the power of 1 down, so that number's going to stay the same. And we reduce the power from x to the power 1 to x to the power 0. X to the power 0 is 1. So -5 times 1 is going to give us -5. When we differentiate whole numbers, essentially you've got x to the power of 0 there, so you bring down a 0. If you multiply by 0, you get 0. So now we've got our differentiated version. Now the maximum and minimum points are the turning points of these curves, and it's when the gradient is actually equal to 0. So by solving this quadratic, we're going to get our coordinates. So in this case, we have to use a quadratic formula. So we have negative b plus or minus the square root of b squared minus 4ac all over 2a. Now a is going to be the coefficient on the x squared, which is 3. So let's swap the a's for 3's. The b is going to be the coefficient on the x, which is -4. So let's swap the b's for -4's. And the c is the number at the end, which is -5. So working all this out, -4 is going to give us a +4. -4 squared is going to give us 16. -4 times -4. And then 4 times 3 times 5 is going to give us 60. That's -5, that's -60. So we have 16 take away -60. So altogether, that's actually going to be 76, because you've got a double negative, so you add them together. And 2 times 3 is 6. So we're going to have to work this out as a decimal. Let's take plus minus to be a plus. So we have 4 plus the square root of 76, and divide that by 6. I'm only going to do this to one decimal place. I won't be able to plot it otherwise, but I'm getting 2.1. Now looking for the second answer, let's take plus minus be minus. 4 take away the square root of 76, and then divide by 6, and I'm getting 0.8, or -0.8. So now we know the x coordinates of our turning points. There's one at around about 2, and there's one at negative 0.8. Now, what about the y coordinates of these? Well, to find the y coordinates, we're going to have to substitute these back into our original equation. So when our x coordinate is 2.1, we need to do 2.1 cubed. We need to take away 2 lots of 2.1 squared. Then we're going to take away 5 lots of 2.1, and then we're going to add 6, and that gives me negative 4. Perhaps we'll call it negative 4.1, but it won't make too much difference to where we plot this. So that's going to be our minimum point. Now, for a maximum point, I'm assuming, take the 0.8, substitute that in. So we have negative 0.8, and we are going to cube it. That should give you a negative 0.512. We're going to take away 2 lots of negative 0.8 squared multiplied by itself. We're going to take away 5 lots of negative 0.8, and we are going to add 6, and that gives me 8.2. So now we can plot those coordinates. I'm going to rub off my rubbish sketch here. I'm going to keep the 3 x-intercepts and the y-intercept that we found already, because they were correct. But what I'm going to do now is add the 2 new coordinates that I found. So we had 2.1 and then negative 4. That's going to be around about here. Don't worry too much about the decimals. It's a sketch. Then we have negative 0.8 and 8.2. So roughly 1 back and 8 up. So roughly here. So now when we sketch this, what we can do is we can start off with our first x-intercept, work our way up. Now we know where our turning point is. Then we can start to come back down through the y-intercept, drop all the way down to the minimum point, curve back up, and what we've got there is a pretty decent sketch. Now, if I wanted to be more accurate at the end, what I might want to do now is maybe substitute in 4 to see where it goes next. So that would be 4 cubed, take away 2 lots of 4 squared, take away 5 lots of 4, and add 6. And that gives me 18. So actually, if I'm getting 18, that's way off the graph by the time I get to 4. So it looks like it's rapidly going to leave this kind of viewing window we've got here before it gets to 4. So something like this. And then it's probably going to be the same at the other end as well. And so now we've got a nice accurate sketch of this. So as you can see, there's a lot of different techniques. Let's recap. So you have looking at the number at the end for the y-intercept. You have factorizing the cubic for the x-intercepts. And factorizing cubic is a pretty involved process using algebraic long division. And then we have differentiating the curve and seeing where the gradient is equal to 0, and potentially even using the quadratic formula to solve that quadratic to get the turning points. So there's a lot going on, but this will be worth a lot of marks. So let's do one more of these. So again, the first thing to do is always look at the y-intercept, really easy to find. That's the position where y is equal to 0. That's always a number at the end, which is negative 4. So immediately we have our first coordinate. The next thing to do is to factorize this. Now, again, that takes quite a while with algebraic long division. So go and watch the video on that if you want to know how. But once you factorize this, you should get this expression. Now, if you made this equal to 0, so when y is equal to 0, we are getting the x-intercepts. So that's going to be x being equal to negative 2, positive 1, and positive 2. So now we know 3 more coordinates when x is equal to negative 2, 1, and 2. They are all when y is equal to 0. So let's plot them on the graph. Now, again, we can get an okay sketch of from that. So we are going to take our line, y is equal to negative 3x cubed plus x squared plus 4x minus 4. We're going to differentiate it to find an expression for the gradient, bring down the powers, negative 3x, but reduce the powers by 1 when you bring it down. Bring down the 2 and reduce by 1. Bring down the 1, so we get a 4. When you reduce the power 1 by 1, you get power 0, which means that you're going to lose the x on this term, and the next term is going to be multiplied by 0 and go away. If we make this equal to 0, we are going to find our turning points. So again, this is going to be a job for the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. A is going to be equal to negative b. So 2 times negative 3 is going to be negative 6. We'll be dividing by negative 6. And in the 4ac, that's 4 multiplied by a multiplied by c. Well, it'll be 4 multiplied by the a, which was a negative 3. C is a number on the end of 4. And then b is the term on the x, which is 2. That'll give us negative 2 and 2 squared. So now we can start to work this out. So 2 squared is 4. 4 times 3 times 4 is going to give us 48, and it's negative 3, so it'll be a negative 48. And 4 take away a negative 48 is going to give us a positive 52, because it's a double negative, so we add them together. And so what we can do now is we can plot this into our calculator and get some answers, and they're probably going to be decimals, given that we've got root 52. Let's take plus or minus b equal to plus, so we have negative 2 plus the root of 52, and then divide the answer by negative 6, and that gives us negative 0.9 to one decimal place. Now let's take plus or minus b minus negative 2, take away the square root of 52, and then divide that by negative 6, and we get 1.5. Now we just need to substitute those into our original equation to get the y coordinates. So when x is equal to 1.5, that will give us negative 1.5 cubed, which will get you negative 3.375. We're going to add on 1.5 squared plus 4 lots of 1.5, take away 4, and that's going to give us a 0.9 to one decimal place. So we can plot that coordinate. Then we'll have a look at when x is equal to negative 0.9. So substitute that in. We have negative, open some brackets, write in 0.9. Then you can close the brackets and cube it, and that's going to give us a positive 0.729. Be careful of the negative numbers there. We're going to add on negative 0.9 squared. We're going to add on 4 lots of negative 0.9, and I'm going to take away 4. And that gives us negative 6. Let's say negative 6.1 to one decimal place. So if we plot that, we're almost going back 1 and then down 6. So we're roughly going to be somewhere like where I'm just highlighting in pink there. Now, if we assume this rapidly approaches this window, we're going to come down like this, hit a minimum point, curve back up, go through the y-intercept, back up through the x-intercept like this. Now, I realize I've plotted a negative version of 5.1. It should be and 0.9. It should be positive. So it should have been there. Then we can come back around, and then it's probably going to rapidly leave the window we're looking at like that. And if you're not sure about the place where it comes in and comes out of the graph, you can always substitute in the next set of values. So x is equal to 3 and negative 3, just to get a bit of a better kind of idea of where they're coming in and out. But what you can see here is I've got a pretty good sketch, and the only substitution I've done is 2 sets of substitution to get the minimum and maximum points. Now, you might be thinking, well, why didn't we just substitute in those points in the first place? Well, if you think about it, you're probably only going to substitute in positive numbers, and we've already got a positive 1 and a positive 2 coordinates on here. So the maximum point was at 1.5. That's not a coordinate you are naturally going to be looking at, because if you're looking at, 0.1, 0.2, 0.3, it's going to take forever to substitute. And particularly negative 0.9, that is not something that typically you would be looking for. So we need a differentiation to kind of guide us to the particular substitutions that we need for the important points. The next thing we're going to look at is a new symbol called the modulus. And the modulus, it just means positive values only. So let's have a look at the modulus in action. So let's do the first one using substitution, but we'll move on to using other methods after this. So we have y is equal to the modulus of 4x minus 8. And it's on both sides of that expression, so it almost acts like a bracket. So we're going to substitute in some values. So let's substitute in x is equal to negative 3, negative 2, negative 1, 0, 1, and 2. So we're swapping the x for these values, and the rest will stay the same. So y equals the modulus of 4 times negative 3, take away 8. And then for the other ones, again, we're all going to have the modulus. Make sure you have a kind of large line for this, so you don't confuse it with a 1. We're multiplying 4 by the x coordinate we're substituting in, and I'm going to be taking away 8 at the end. So let's have a look what these are equal to. So our first one is 4 times negative 3, which is negative 12. And we take away 8, and we get negative 20. And so what's going to happen with this is, because it's the modulus of it, I'm not going to write down negative 20. I'm going to write down positive 20. Perhaps another way of explaining this and showing it is that, yes, the answer is negative 20, but we want the modulus of negative 20, which is a positive only version, which is 20. And we're not going to be able to plot that on the graph because we only go up to 10. Let's have a look at negative 2. 4 times negative 2, take away 8, should give us negative 16. So the modulus of that is a positive 16. Then we have 4 times negative 1, take away 8, that's negative 12. So we write down as our answer a positive 12. 4 times 0, take away 8, gives us an answer of negative 8, but with a modulus, so we write a positive 8. Moving on to the next two, 4 times 1 is 4, take away is negative 4. The positive version, so just positive 4. And then 4 times 2 is 8, and take away 8 gives us 0. The coordinates we'll plot on the graph here, we've got x is 0, y is 8, x is 1, y is 4, and we have x is 2, y is 0. So let's plot those. And what do you think here is, we are actually allowed negative x numbers in this. It's only the y equals that's going to be positive numbers only. So far, we have what looks like a normal line. And you might be tempted to just draw a line from here. And if I sketch the line, then it's going to look like this. It looks like it's kind of going down by 4 each time you go across by 1. So there's our line. But this is actually the wrong answer. Now, the reason for that is let's have a look at x is equal to 3 and 4. So we're going to substitute in 3 and 4 for x. It's y is equal to the modulus of 4 times 3, take away 8. And y is equal to the modulus of 4 times 4, take away 8. So 4 times 3 is 12, and 12 take away 8 is a positive 4. Well, we didn't even need to make anything negative there. And then the second one, 4 times 4 is 16, and take away 8 is 8. Seems easy enough, and we've got our coordinates. X is 3, and y is 4, and x is 4, and y is 8. Let's plot them and see what happens. So I want 3 across 4 up, and want 4 across 8 up. And now you'll notice it starts to look very odd, because now if I draw a line, I'm going to draw it in green this time, it's going to come down, it's going to hit the x-axis, but it's going to refuse to take any negative values. And so what's going to happen is it's going to bounce back up like this. And this is the feature you see in modulus graphs, where when you try and draw it using normal methods, you are going to get the wrong answer because it's going to bounce off the x-axis and only take positive values. So you get these kind of V shapes when you use the modulus. So let's have a look at a few more modulus questions. Now, we don't want to plot these doing 8 substitutions every single time. That'll take forever. So we can just look at the y-intercept like we looked at before. The y-intercept is -1. But remember, because of the modulus, the y-intercept is going to be the modulus of -1, which means x is equal to 0, y is going to be equal to 1. It's going to be positive only. And now we can plot that coordinate. So that's our first one. The straight line graphs, you look at the gradient. The gradient is -3. So what that means is for the original line, and I think what I'll do here is I will start off plotting the original line. So we will plot -1. If our gradient is -3, it means that every time we go 1 to the right, we're going 3 down. There's going to be a pattern like this, and in the opposite direction as well. Every time we move once, we actually move 3 times in the other direction. So just looking at the gradient and the intercept, this is the line, -3x minus 1. Let's plot it. Let's sketch it out. And while I'm sketching this line, you should be drawing these with a pencil and a ruler to get them nice and straight. So when I label this is a line y equals -3x take away 1. Now, that isn't the line we want. We want the modulus of this line. We want the positive version of it. So all that happens is, with the modulus of this, if I do this in another colour, the positive part of this is fine. Now, all these are negative x coordinates. We're talking about on the y-axis. Y equals, so with a modulus, we want positive y's. All of these are positive y values. But then when we hit the x-axis like this, what's going to happen is the line's going to bounce up. So we're not going to go through -1. We're going to go through a +1. We're not going to go through 1, 4 and 4 down. It's going to be 4 up instead. And so it's actually going to go like this. The same pattern. Move across once, you're going 3 up. So again, we get this V shape. And now that is the modulus of -3x minus 1. See the difference between the two graphs. One of them is just a normal line, and the other one has a bend in it as it bounces off the x-axis because it's not allowed to have negative y coordinates. So let's have a look at another example. So again, first thing to do is plot the normal line. Ignore the modulus. Our y-intercept is at -3, so let's draw that on. And our gradient, it's a half x. And a bit more detail about gradients. Gradients are changing y over the change in x. So if it's a half, that means your y movement's going to be 1 and your x movements are going to be 2. So if I do a move of 2 on the x-axis, it'll be a move of 1 on the y-axis. And we'll get this kind of pattern like this. Each time moving 2 on x and 1 on y. Then you can also move in the opposite direction to get your straight line. And so what we have here, this is the regular line. So let's just sketch through it and let's label. This is y equals half x minus 3. Well, we want the modulus of it. So when we find the modulus, that means we do want to keep the positive version of this, so the positive half going down to the x-axis. But now, rather than you think about your gradient going kind of down 1 and across 2, it's going to be up 1 and across 2. And so that gradient pattern goes in the opposite direction like this. And it's essentially a reflection of the line below. You'll also notice the y-intercept. Now it's not -3, it's going to be a +3. Now again, if we're using a pencil and a ruler for this, I'm just going to sketch it quickly to get the idea of how to draw it. Then the purple version of this is the modulus y is equal to the modulus of half x minus 3, only the positive coordinates. If you get confused about how to plot the positive part, another method might be to take a random coordinate. So this one here is going to be 2, -2, and then just plot the positive version of it to +2. You can take another coordinate. Let's look at this one here. This is going to be -4, -5. So then above it, you're going to have -4 with a +5. And again, the key thing here is that you are going to be allowed negative numbers for the x coordinate, but you're not allowed negative numbers for the y coordinate if it's written like this. Moving on to our next example. So straight away, we can see the y-intercept is -2. Now, we're not allowed negative values for a modulus, but we're going to plot the original line first. The gradient is -1/3. So we take the gradient to be the difference in y over x, then that's going to be 1/3. So we move 1 to the y-axis, we're going to move 3 times on the x-axis. Now, it's negative, we can make either one of these numbers negative. Usually making the y negative makes a little bit more sense. It doesn't matter though. So starting with our y-intercept, we're going to move down 1 on the y-axis and across 3 on the x-axis. Down 1 on the y-axis and across 3 on the x-axis. And so we start to plot our line like this, and then don't forget to go in the opposite direction. So this is our original line. So let's try and plot it. Again, use a pencil and a ruler to get this nice and straight. And really important when using this method, label it. Make sure it's not misunderstood that you think that this is the answer, this is a modulus, because it's not. Now we can take the positive part of this to also be part of the modulus version, but it's going to bounce off the x-axis. Now, if we look at the gradient's moving down on the y-axis and across 3 on the x-axis. So when we hit the x-axis, it's going to go in the opposite direction. It's still going to go across 3, but now it's going to go up 1 each time. So it's going to look like that. Effectively, once you're bouncing off the x-axis, if it's positive, make it negative, and if it's negative, make your gradient positive. And now we can label our answer. And again, this is really important to make sure it's clear which of the lines is working out and which of the lines is the answer. So the answer is a modulus -3 x take away 2, and it's labelled correctly. So now let's have a look at our final modulus example. So we're going to plot the regular line first. So we'd have a look at the y-intercept, which is going through +3, and then we'd look at the gradient. The gradient is a difference in y over the difference in x. That's going to be 1/4. It's negative. So every time we move once on the y-axis, we're going to move 4 times on the x-axis. So that's down once for y, that's going to be across 4 for x. Again, down once for y, across 4 for x. We're going to be more accurate, we can even go halfway. So you can see that maybe we can go down a half and then across 2 to get to the end, because we can't go across the full 4. Remember to go back in the opposite direction, up 1 across 4, and then we can try and plot the line. Again, use a straight line and use a ruler. Make sure you label what the line is. This line is y equals -half x plus 3. And then we think about the modulus. Which part of this is positive? Now, for this one, actually, the entire line that we can see is positive. So this segment that we can see between -10 and +10, this is also y equals a modulus of -4x plus 3. There's no difference between the two lines for this section we can see, but you can see that it's getting quite close to the x-axis by the time we get to 10. So when x is 11 and 12, that's when the line would bounce off the x-axis, and you get the pattern you'd see with the previous questions. So what I'm trying to show you here is that the modulus isn't always going to be different to the line itself. It's going to cross over the x-axis in the kind of viewport you've got, in this case between 10 and -10, for you to be able to see the difference between the two lines. So the lines are different because we can't see them in this part of the graph. The last thing we'll look at is solving equations using the graph. Now, we have a really easy equation here. 5x is equal to -5. And I know you can do it in your head, and I know the answer is x equals -1. But we'll see how we do it with easy ones like this, and then build our way up to more difficult ones. Now, the way you solve this is we take the left-hand side, 5x, and turn it into a line. Y is equal to 5x. Then we take the right-hand side, the -5, and we turn that into a line. Y is equal to -5. Now, the easiest one to plot is y is equal to -5. It's going to go through -5 on the y-axis, and it's got no gradient. It's got a gradient of 0, so it's going to be a straight line. Let's label it. And then let's have a look at the second line. Y is equal to 5x. Now, the gradient is a change in y over the change in x. We have 5. If you only have one number, it's not written as a fraction. then put a 1 in for x, because 5 divided by 1, 5 over 1, and 5 are all the same thing. Now, it's got no y-intercept, it's got no plus or minus, so it's going to be going through 0. And so the change in x and y, if y changes by 5, x will change by 1. And so we can start to plot the line like this, and also go in the opposite direction. Then we can draw a straight line through. Now, why are we doing this? Well, you can see that the two lines cross over, and look at the coordinate of where the two lines cross. They cross at -1, -5. Now, each coordinate has an x and a y value, and you can see that the x value of this is -1, which is the answer to the equation. 5x is equal to -5. So then when we have a look at our coordinates, the x coordinate is -1, and that is our answer. So that's how you solve equations using a graph. Moving on to our next example, we have 3x minus 1 is equal to -10. Again, I can do this in my head. I know that x is going to be -3. And again, doing the algebraic method, adding 1 to both sides, dividing both sides by 3, obviously that's a lot easier. But getting to show you this method on easier questions so you can do them on harder ones. So you take a look at the left-hand side. We have 3x minus 1. So I draw the line y is equal to 3x minus 1 for that line. On the right-hand side, we have -10. So we want to write 9 is equal to -10. So then we plot the two lines. Now, y equals -10 is going to be the easiest one. That's going to be 10 down. It's got a y-intercept of -10. It's going to be here, and it's got no gradient, so it's going to be a straight line. Label it, and then have a look at the other one. We want y equals 3x minus 1. The y-intercept is going to be at -1. And the gradient, if the gradient is the difference in y over x, then the gradient is a 3. So it's going to be 3 over 1. If you move once on the x-axis, you're going to move 3 times on the y-axis. And so we can plot a pattern to draw a line across. And also in the other direction. Draw your line through, label, and look at the point of intersection. Two lines intersect at this point. That's -3 on the x-axis, and it's -10 on the y-axis. That means that the answer to 3x minus 1 equals -10. X must equal -3, because the x-coordinate of the point of intersection is -3. Moving on to our third example, on the left-hand side, we have -6x take away 12. We need to plot y is equal to -6x minus 12. With the gradient, it's y over x as always, so that's going to be -6 over 1. It'll be over 1 if there's no denominator. And the y-intercept is -12. So from the -12, on the y-axis we can go down 6 and across 1. Well, that'll go off the graph. We could do half of that and go across 6 and down 3 and across half. In the opposite direction, it's going to be 6 up and 1 in the negative direction. So just follow the pattern of 3 and 1 in the wrong direction if we're going from right to left. And we start to build up the pattern of what we're plotting. Draw a straight line through and then label. The label being really important so you know what you've done and the examiner knows what you've done. Then look at the right-hand side. We've got a 6. That's going to be y is equal to 6, which we really use to plot. The y-intercept is at 6, and there is no gradient. So it's going to be a flat line. Again, we label it, and now we look for the point of intersection. That's at -3 and at +6. So when we're looking at the equation, -6x minus 12 is equal to 6. We can say that x is equal to -3 without doing any kind of algebra rearrangement or inverse operations, because the x-coordinate of the point of intersection is -3. Next, we'll look at solving simultaneous equations. So we have two equations. Now, there will always be a rearranged by y equals. So you need to solve simultaneous equations on a graph. You first have to rearrange them so it's y equals something. Now, it's the same method what we've just been doing, because if you think about it, both these equations are equal to y. So you can make them equal to each other. So really, we're looking at 3x plus 8 is equal to -3x minus 4. And that's a version of solving via substitution. And we could work that out and get the x-coordinate. But another way is we could just draw the two lines. So the first line is y equals 3x plus 8. The y-intercept is at 8. And the gradient y over x is going to be 3 over 1. So if we move 3 up on the y-axis, we're going to move across 1 on the x-axis. And then we could build up a list of coordinates using that sequence, and we can plot the line. Make sure it's labeled to know which one's which, and then move on to the second line. Y is equal to -3x minus 4. So the y-intercept is at -4, and then looking at gradient, gradient is a change in y over the change in x. The gradient's -3, that'll be -3 over 1. So from our y-intercept, if we go down 3 on the y-axis, we're going to go across 1 on the x-axis. And of course, we can do that in the opposite direction. And you can probably see already where the point of intersection is. But let's just finish this off properly and draw our line. You see both these lines have got the same gradient of 3. Just one of them's negative, so it's going in the opposite direction. We'll label it and find the point of intersection. It's at -2, -2, and the x-coordinate is -2. So we can say, firstly, if it was the combined equation like I showed at the start, we could say that x is equal to -2. If we had the simultaneous equation that we actually did start out with, so they started out being written apart for us, then we need both x and y values. So we'd say that x is equal to -2 and y is equal to -2 also. So it all depends on how the question's phrased. If you get it in the blue way where there's no y, you don't need to write a y coordinate. If it's the purple way where there is a y, then you do need to write a y coordinate. Our final example is another simultaneous equation. So let's take the first equation, y equals 5x minus 8. So we know this is going to go through -8 on the y-axis, and the gradient is 5. The gradient is changing y over x. That's going to be 5 over 1. So the y change is going to be 5, and the x change is going to be 1 each time. Then we can draw a straight line through, and we can label. Then we do the same thing for the second equation. We can see that the y-intercept is at -1, and the gradient, changing y over x, is going to be -2 over 1. So if the y-coordinate's going down by 2, the x-coordinate goes across by 1, and we can keep repeating that sequence. Then we want to draw a straight line through and look for the point of intersection. PhET label a line as well, and the lines intersect at -1, -3. So now you've got two options for the answers. If you've been given this as a simultaneous equation, which is the way this was presented, then you've got to write an answer for x and y. So we're going to say that x is equal to -1 and y is equal to -3. If these were combined from the start, like our first few examples, so we had 5x minus 8 is equal to -2x minus 1. So it's written more like a normal equation to solve with one variable. And they're both equal to y, so you can make them equal to each other. Then we just write down x is equal to -1, because in our answer we've got our x and y coordinates, and you're only being asked for the x coordinate in that scenario. So again, there's two ways to ask these questions, so tailor your answer to the particular way it's been asked. And again, the last thing to think about is these simultaneous equations have been y equals at the start, but you might get simultaneous equations that you have to solve graphically that are in a different order. You have to rearrange them to make one y be the subject.
Ouch! This is why in some videos I've explained scratches.